SIwave is a power integrity and signal integrity tool. The focus today is on the resonance mode solver, which is this guy, compute resonant modes. The main reason for doing resonance calculations is to identify the best location to put decoupling caps in power planes. The size of the power plane is determined by the expected maximum current and the allowed maximum voltage drop. However, even the best design doesn't have enough capacitance to keep the impedance at low values for a broadband spectrum. The spectrum of the power plane is derived from the current pulses. Power planes need decoupling caps to extend their bandwidth beyond. So SIwave can import the following types of CAD files: ODB, IPC, EDB, DXF, and GDSI. When it uploads any file, it will import with it all kinds of information like the material, the stack up. You can also see the stack up, all the information about the stack up, the dimensions, the materials, and all of this. And also all the nets. Any process in SIwave, any process, any solver, DC, PI, signal integrity, anything, it always starts by selecting the solver first. Once a solver has been selected, SIwave generates a dialog box that looks like a form. The user needs to check the form and fill up the missing information. For example, if I excite this compute resonant modes, this is what I get. I get a very simple dialog box where I need to enter the minimum frequency and the maximum frequency where I'm looking for resonance inside my design, how many I'm looking for. I can give the simulation a name. And you have also here other solver options. If you click on it, you can specify the accuracy of the solver. Do you want it to be optimum speed or optimum accuracy, or do you want it to be balanced? Usually we keep it as balanced. Now we launch the solver. So if you launch the solver, it will start solving and we will get the results like this, one of these. Before we start talking about the results, let's explore what happens if we do not have any decoupling caps in our model. From the PI analysis, which is one of these, that we described in another video, we can plot the Z11. We explained in that video that it's important when you solve a power plane to add the equivalent circuit of the VRM and read the impedance from the load side. That is the right way to study a power plane. So for example, let me look at here. If I click on this, I say plot magnitude. Look at the Z11. This is what we see. So as you can see, we see a significant resonant, right at 0.2 gigahertz, 206 megahertz. And that's on the power plane 1.2 volt. We would like to extend our Z bandwidth beyond this value. So how are we going to do that? By adding decoupling caps. But where and what value and how many? The resonant mode solver will only answer for you the first question: where to put the decoupling caps. By the way, from this plot, we determine the range of the bandwidth, the range of frequency where we are looking for our resonance. So for this case, for example, we're looking at a resonant at 200 meg. It means I want to solve something within this range to be able to see this mode. Now, the definition of the resonance is the frequency at which the impedance is very high. But physically, what does it mean? For people working with antenna, it means that at this frequency, the power plane becomes like a perfect antenna. It radiates lots of its energy out and also accepts any signal, any noise from outside at that frequency. Nothing you inject at that frequency will reach the other side. So if there is a sudden demand for lots of current, the system cannot deliver that. That's another reason why it should be suppressed, why we need to suppress this one down. So once the solver is done, now we would like to look at the results. So if I click here and I say view results, what you're gonna get is a list of all the resonance in the PCB in the band of interest. Here we get the real part that represent the real resonant frequency. So as you can see here, 194, that's the first one, 194 megahertz. And the imaginary part stands for the losses or the damping factor of the resonance. The K is defined as the free space wave number. And it's simply, the wave number is simply equal to the frequency, the real of the resonant frequency multiplied by a constant factor, which is 2 pi over the speed of the light. So there's a constant factor between these two. So if you divide this value over the frequency, you will end up with a number closer to 20.95 something. Now the wave number, the wavelength is simply the wavelength in free space at that frequency. So these three represent almost the same kind of information. There is nothing new. And the Q factor represents how sharp is the resonance. So if you want to look at the formula of the Q, it's a function of the absolute value of the resonance, which is practically the real part, divided over 2 times the imaginary part. So it's a function of both of them. Unfortunately, from this, you cannot tell where is this resonance. Is it on the power plane of interest, or is it on another power plane? Also, you cannot tell how bad it is. Like, you can tell from the Q how sharp it is, but you cannot tell if it is big, huge, or small, weak. The only way to tell is by looking at the Z11. That's the only way. So to be able to tell where each one of these resonances exists, unfortunately, the only way is to display the field. Now, because SIwave cannot tell where this resonance is, it can only plot field between 2 layers. So you have to select 2 layers. For example, in my case here, I will select the VCC and the ground. And if you click compute, you're gonna get a list of this list where you have 23 different plots. Each one of them represent one of these resonances. So we're plotting each resonance between 2 layers. Now, if I have a second ground, I'm gonna select the second ground. I'm gonna ask SIwave to compute the field between VCC and the other ground. And it's gonna create another set for me. As if you can see, I have so many sets. In my case, I don't have another ground, but what I can do is I can plot between the surface and the ground, and I can plot between the base and the ground. And as you can see, I have the first set, it's the base and the ground, surface and the ground, and VCC and the ground. And in each one of these sets, I have 23 different plots. Now I have to go through them one by one, unfortunately, in order to be able to know where they exist. So let's focus on the VCC with the ground, because that's where our plane is, and that's where we care to see the field. So when I select one, practically I selected this resonance. So what we're gonna do, we're gonna hide a little bit the structure, and we're gonna display the field. That's how we activated the field. I'm gonna hide the structure, display only the VCC. So the first resonance, we don't see anything. There's almost nothing. We click the second one and suddenly we see red, and this power plane is our 1.2 volt. It's the power plane of interest. Great, so if we go 3, we see nothing, 4, nothing, 5, nothing, 6, we see another kind of resonance, but unfortunately it's not in the power plane of interest, it's outside. It's in what we call 3.3 volt power plane. Great, so now we know that 6 belongs to that power plane, and so on. If you go 7, the same thing like 6, it's in the 3.3, it's not in the 1.2, 8, 9, 10, and so on, until you go to the end. And for example, 23, again, you see most of that resonance is in fact outside our power plane of interest, which is the 1.2, the one in the middle. Let's go back to our resonance at 6. So we click on the 6th one, and we look at this resonance on the 3.3. And what we would like to do is we would like to do phase animation, which is very important because it will tell you how this resonance is behaving, and it will show you more areas of interest. So we start playing the animation. And as you can see, we have 2 red spots, one at the bottom and one at the top corner. Why we care about these red spots? Because if I want to put decoupling caps, it's there where I put these decoupling. These are the first 2 places where I need to place decoupling caps in order to suppress the red area down to a green kind of area. You can also, while doing the animation, you can also rotate your structure and see everything in 3D. It's a nice way to look at things. Now, let's go back, stop this one, and let's go back to our number 2 resonance, which we discovered that exists in the power plane of interest. By the way, this is the scale. You can double click on the scale. You can change the setup of the scale. You can go with log or log scale. But usually for this kind of applications, linear scaling will do the job. That's all what you need to see. You don't need to go to log scaling. Now, because the whole area is red, of course, we can do animation again. Let me do animation here also, just to make sure that I understand the behavior of the resonance time. You see, this whole thing is red, goes up and down in terms of amplitude. Notice one thing, that for any resonance I select, the amplitude, the maximum amplitude is always 1 volt. The lower is -1. And unfortunately, because SIwave normalized everything to these values, they mean nothing. You cannot tell from them that this is a very bad resonance. Even from the size of the red area, you cannot tell. So the size of the red area just tells you that you need to put capacitors, decoupling caps, everywhere it's red. So in our case here, we have to put power planes, we have to put decoupling caps, sorry, around the edge and also in the middle. That's all. That's the only information we can get out of these plots and out of this table. So as I said, from these plots, you cannot tell whether this is a good or bad resonance. The only way to do it is by going back to the plot of the Z11, and only there you can see the resonant point, how bad it is. So in this case, we can tell that this is very bad. So now we would like to add decoupling caps. So I'm going to add the decoupling caps. Let me show you where we added decoupling caps. As you can see, we have them around the edges and also in the middle, which makes sense because the red was covering this whole area. So the first thing we were going to look at is the results of the Z11 plot. Plot magnitude. This is the Z parameter. And as you can see, we are somewhere around this area, around 200 meg. So we're going to move the mouse until we reach 200. Much, no, 27. Of course, you can double click here and move it manually to 200. 2065 E9. And as you can see, it's around 0.1223. If you remember from the first plot, it was around 21. So we suppressed it from 21 to 0.122. So we achieved the goal to suppress the resonance using decoupling caps. Now let's run the resonance to see what's happening with the resonance. So if we do that, and we go with caps, view results, we're gonna see the same kind of resonance. It doesn't mean suppressing it that the resonance will disappear. It will still be there. And again, I plotted the feeds in all of them between VCC and the ground, and now we can go and look at them one by one to make sure that we have the right resonance. So this one, number 3. So I go to number 3. You see, I have the resonance, and now the red area is covering small section of my power plane. Of course, as I said, unfortunately the cross section or the area of the red doesn't say anything, doesn't mean anything. You could have something that's very small, yet it's covering the whole power plane, as I'm going to show you with other cases. So you can go 3, you can go 4. So even 4, which is 203, also is a resonance now inside our power plane. 5, 6, 7, 8, 9. So now you are asking yourself so we ended up with more than just one resonance. Before we had only one resonance at 200, and now we have more. Yes, adding decoupling caps unfortunately create more resonance, but these resonances are so small and detectable. And I'm going to show the Z impedance. You will see some notches, but they are very small, suppressed. So let me go back and show you the Z11. So as you can see here, you see lots of notches all over the place, but they are very small. They are very small. Their value is still at 0.12 something. They are not 21. Now, in addition to this, you also notice that we generated more resonance at lower frequency, which is this one and this one and this one. So if I click markers, I can see that I have also resonance, which look also small, way small. The impedance still way small, but they are still resonance. So if I go and I want to know if SIwave is able to detect these SIwave, I'm gonna run my resonance, but I'm gonna change the band of interest. So I'm gonna ask for resonance within that band at low frequencies. So what we are going to do is to run the resonant mode solver at these low frequencies, and we're gonna look at the fields. So if I open the results, I already have the results. Now I can ask for the field between VCC and the ground. I say compute. Remember, you have to click in this area, not in this area, to see the field. So 1, 2, no, 3, no, 4, 5, and 6. Oh, so 6, it's one of these resonances that exist in our power plane 1.2 volt. And as you can see, it's covering the whole thing. The whole thing is red. Yet when you plot Z11, it's very small. It doesn't have a significant value. Can go to 7, 8, 9, 10, 11. 11 is another resonance, and 11 is around 2.9 megahertz. Then we have 12, 13. 13 is another one that's around 7.9. So these are the small resonance that we saw in the Z11 plot. So if you are not happy with them, even if you're not happy with them, you can come back here and see exactly where they exist. And of course, as I said, remember to do the phase animation. Don't just rely on the plot at 0. Do the phase animation just to make sure that the red area doesn't go to other places. Because if it goes to other places, then you need to put decoupling caps in the other places. And that's how you do to suppress these resonance, even the small ones, more and more, if you want, if you're not happy with their behavior. So practically, this summarizes the things that you can do with the resonant mode. It allows you to display the field of each resonant. It can tell you which resonant you need to worry about. And with the help with the Z11, you can tell if it is good or bad resonance. It's something you need to worry about and ignore, or something severe you cannot tolerate. At the end, we don't want to suppress every resonance. We only want to suppress the ones that make the Z impedance exceed specific value in the band of interest. There are other things that you can do is look at the profile, of course, which will tell you more information about how much time was spent and the mesh size and all of these information. These are important when you are comparing the solution of two models, or you are comparing the solution of the same model at different times. It tells you whether you are doing things, or whether the solver did something right, or no, the solution looked weird. It took, for example, faster time to solve. Doesn't make any sense. It should spend the same amount of time if it's the same mesh. Also, you can verify your simulation properties. And what the simulation properties is telling you is reminding you what are the minimum and maximum frequency number of modes that were used to get this solution. So in the future, if you come back to your solution and you would like to know what exactly was your setup, you can use this